Okay, welcome to this next video on data visualization. We're going to focus for this video on using the visualization tool ggplot2, which is something that's going to come in a lot of handy when you want to visualize your graph, especially for inferential statistics. So if you want to create bar plots, line graphs, anything at all that you might want to put into a scientific paper, then using ggplot2 is going to be the way to go. And it's also going to be something that's going to be beneficial to learn if you still want to learn stats and you want to learn how to use R, but you're planning to do something that's more industry related because of its usefulness in terms of being able to visualize data through a number of different methods. So with that said, we're going to focus a little bit today on doing visualization using ANOVA in particular. And the reason I want to focus in on that is because while we talked a little bit about how ANOVA works, we didn't talk very much about how we can estimate group differences after we account for different variables. And so we're going to spend the first part of this lesson here today on understanding how we can do that in R. So first, let's go ahead and let's open up our data to RStudio, or excuse me, open up our copy of RStudio, and we'll go ahead and we'll get started. So just as always, let's go ahead and let's load our data. Just like before, we can just use the pacman function to be able to load the packages that we want to use. Set your working directory to where your data is located, and then let's load that data set that we've been working with thus far. So thus far, what I've really been discussing is I've been discussing how to do ANOVAs and ANCOVAs from a single time point. However, one thing that we can do as well is we can look at ANOVAs from multiple time points, and that's going to be something that oftentimes is going to be of more interest to us, especially if we're doing something like an intervention or something along those lines. So when this is the case, what we're going to need to do is we're going to need to manipulate our data into a wide format. So if we have more than one time point and we want to look at differences between groups from time point 1 to time point 2, this is going to require us to manipulate the data into wherein, rather than having time point 1 going all the way down and then we just have three different T001, T002, and so on and so forth, we're going to need to have each individual time point be labeled separately. So this data would be in a long format, and we're going to need it into a wide format. Now, the way that we do this is pretty straightforward. I'm just going to walk through each part of the code that you would use. So first, what we're going to have to do is we're going to have to determine what are the parts of our data that are varying. That is, what varies over time. So if we just go ahead and we look at the different column names from our data, again, we can see that this is our ID variable, this is our time variable, and then we have what we consider to be varying components of our data set. In this case, let's just keep it simple, and we're going to focus on ADAS-Cog and meters walked, both of which we're assuming vary from time point 1 to time point 2. And those values do differ within this data set. So we're assuming that we collected those data 3 different times, and each time the data could vary from time point to time point. So once we've done that, we're just going to create this subset of data called varying, and then we're going to create another subset of data called baseline. And all that is this just means that we're subsetting the data here to just use the data frame from data 2, and we're not using the variables 10 and 11. So that is, we're not including ADAS-Cog and we're not including meters walked, and that's because those data vary over time. We're assuming that these data are all the same all the way, throughout this all 3 time points. And so we're creating that separate data set. So if you look at varying, this just includes time, ID, time, ADAS-Cog, and meters walked. And then if we look at baseline, it's just all the baseline variables that aren't varying over time. And that's just 40 values, whereas varying is 120 observations. So how are we going to combine all of these? Well, to do so, what we're going to have to do next is we're going to have to split our data even more. And to do this, we're just going to take our varying time sets or varying time data, and we're going to split it down into 3 subsets of data based on the time point. So baseline, midpoint, and final. Once we've done that, we're going to go ahead and we are just going to add something to the very end of each column within the varying time data. So what this means is that within the column names of varying.1, we are going to add a dot one to each variable at the end. So if we look at varying.1 right now, there's nothing at the end of this. But after I run this command here, if we look again, oh look, now every single variable has a dot one attached to this. And this is going to help us distinguish between the different variables that we're using within these data. And the same thing applies to varying.2 and varying.3. Now we're going to use the package dplyr for this, or dplyr. And for this, we are going to go ahead and we're going to transform these data into a wide data frame. So what does this what does this mean? Well, what this means is that we are going to join each of these data sets, baseline, varying.1 by id.1. Then we're going to left join id to id2 and id3. And basically what this means is that we're just assuming that these are all the same IDs. So ID is equal to ID1. There's no differences here. But it's just that the other variables, we're going to join those into the same data frame. So right now, if you're paying attention, what we have is we have baseline, varying.1, varying.2, and varying.3. Those are our 4 data sets. And for this, what we're doing now is we're just going to combine them all into one data set. So we just use that dplyr command, and we're going to join them all together. And then we just are unattaching the dplyr library, just so that way it doesn't screw up anything that we're trying to use later. And so now if we look at these data, now we have all the stuff we need for our analysis. We now have time point 1 for everybody, but this is for group, age, sex, education, height, weight, BMI, and these are all assuming that these are at baseline. They don't change over time. But I now have my baseline variable. I have time point 2, and I have time point 3. So I now have all this stuff included in one data set. And if you really wanted to, you could clean this up and get rid of time.1, time.2, and time.3. It doesn't matter for what we're discussing here today. We're just going to be focusing in on how we can use this to do a ANOVA or ANCOVA, wherein we control for baseline differences. Okay. So one way that we could be looking at group differences, perhaps in an intervention, if we wanted to, okay, would be for us to just do a regression or a ANOVA, wherein we look at ADAS-Cog performance at final, and we were to just look at group differences. Okay, so we're just looking to see if one group did better than the other at the last time point. Makes sense. It's an easy way of looking at it. There's just one teensy-weensy problem, is that while is of course obviously there are no group differences, which is okay, but what is more worrisome is we're not accounting for what happened at baseline. So for instance, somebody could be doing really well at baseline and then they got worse at final, or somebody could be doing really well on ADAS-Cog at baseline, then they do about the same at final, or any number of different variations. So it's hard to know whether there was any difference or effect of an intervention from time point 1 to the last time point. So a way that we often account for this in randomized controlled trials, wherein we're just looking at differences from baseline to follow-up, is we control for group differences at baseline. So in this instance, what we're going to do is we're not just going to look at group, but we're also going to account for baseline ADAS-Cog performance, so ADAS-Cog.1. And so now we add this to our our ANOVA, and now now this becomes an ANCOVA, wherein we're looking at whether there are differences between groups at final after accounting for baseline. And so from here, what we can do is we can see that while there is no effect still, we are now adjusting for our baseline differences. And so that seems to be, and that is typically what's suggested for any intervention or randomized control trial. That is the standard. You need to account for group differences at baseline. And as well in most pre-post studies as well. You typically want to control for baseline in these studies. Okay, but like I mentioned before, we still don't know what the group differences are. This is kind of difficult to read, and although we can figure this out. So from here, what this is suggesting is that if we were to control for mean ADAS-Cog, so whatever that may be, then that's going to, for instance, a 0 on ADAS-Cog is going to add nothing to this model at baseline. But if you have and if you're in the intervention group, then that seems to suggest that you will score about 0.22 points lower than the control group. So 10.08 minus 0.22, whatever that is. I think it's like about 0.98 or something, 96 or something like that. That's going, or somewhere around, or 9.88, somewhere around there. That's going to be the score for the control group. But there's a way easier way for us to do this, and this is using something called the least squared means, or estimated marginal means. So we can use LS means procedure for this. And so to do this, we just need to go ahead and we need to call the LS means procedure. So for this, you're just going to load that package up, and now what we can do is we can look at group mean differences quite easily. So for this, we're just going to call that same ANOVA that we just ran, and it looks like it's and from here we just need to call the group function, and now we get a better idea of what somebody's baseline was. So again, here we see that the estimated group for the control group was 11.2, and the estimated mean for the intervention group was 10.9, and this is after accounting for baseline ADAS-Cog performance as well. So those are the group differences at final. So that's quite nice and easy. But what if we're interested as well in trying to understand whether there was a difference between groups, or we want to at least look at whether there is a difference between groups and we want to have a better understanding? Well, obviously we can go 11.2 minus 10.9, but that's not necessarily going to tell us if it was a significant difference between groups. And so the way that we can do this is with a contrast statement. And so to do a contrast statement, we're just going to, we can do this one of several ways. The easiest way to do this is to just call this something. So I'm just going to call it lsmeans.1. And that's going to save it right here. And then I'm just going to run a contrast statement using this lsmeans.1. And from here, I'm just going to say, okay, I want you to treat this as if I'm trying to look at the treatment versus the control group. And adjust, that just means am I going to adjust for anything? That can include things like Bonferroni or something to that measure. And then I'm able to look at group level differences. So as to be expected, there's about a 0.22 difference between groups. However, this is not statistically significantly different as we would expect. Now, if we want, we can also add in a confidence interval to this statement as well. So for instance, if I want, I can just take this contrast, and there's a couple different ways to treat this, but the easiest one, again, is just to create a separate statement, and then I can just go conf int and then contrast dot one, and then parm. This is just saying the parameters that I'm interested in, and then level equals 0.95. So a 95% confidence interval for this contrast statement. I'd like to know what is the lower and upper limit for this contrast statement. As we can see, the differences between groups are quite large, and they cross zero, thus leading us to have a p-value that's not less than 0.05. Okay, so I've shown you how to do estimated marginal means, how to do the contrast statement, and a little bit more detail on doing group level differences and controlling for baseline at group. But like we talked about at the very beginning, today we're also going to focus on data visualization. So the reason I wanted to share this with you is so that way we could go through how we could explore these ANOVA differences between groups. And so to do this, now that we have these data already run, is now we can make them into a data frame so we can actually visualize that. So for instance, let's just go ahead, we're going to create something called LM frame. And to do this, I'm just going to take that ls mean statement that I just ran just a few minutes ago, and I'm just going to turn it into a data frame. So the easiest way to do that is to just go lsmeans.1, or I could just take this statement and I could run it right back down here. So we'll just do that. And now I've got myself a nice data frame. Or I did have a data, or excuse me, we're one step away from doing that. So one thing that we do need to do is rather than just that statement, I also need to make sure that I say that this is to be treated like a data frame. And now, if I look at this, I now have this nice data frame to look at. So control, intervention, ls mean statement. So the estimate for the control group, the intervention group, standard error, degrees of freedom, and the lower and upper confidence interval. Okay, so now that this is in a nice data frame, now I can start using ggplot to explore, to visualize these data or visualize group differences. So the first thing we'll do is we'll just create a basic plot for this. And so to do this, I'm just going to go ahead and I'm going to call that data frame, the lm.frame, and then I'm going to take x equals group, y equals ls mean. And again, if we just look back at this data frame, we've got these as my variables now. And then from here, I'm going to add that I want this to be a bar plot. Stat equals identity. So what this does is that this just says that I want you to place this the bar directly over the position of over each individual bar, rather than them being stacked one over another. So really quickly, I just need to look through the code again, and I can see that I'm missing that I was missing a parentheses in the right place, and now I've got this running, and then we should see a nice bar plot that shows up over here. And so that looks pretty basic. I mean, obviously it's not the nicest looking thing, but we can add some stuff to make it look a heck of a lot nicer. So in order to do that, let's go ahead and let's first start by adding labels. And so to do that, we just use labs, and then x equals whatever we want it to be. So I'm just going to say intervention group. And then for the y-axis, I'm just going to call this change in ADAS-Cog. I can also just go ahead, and after a comma, I can just go ahead and press enter, and that's going to bring it down one level. But it should still run the code all as one. And now, as you can see, I've got titles to everything. It's going to be a lot nicer to look at in that way. But, you know, one thing that I don't like personally is I don't like the width of the bars. So one thing that I'm going to add to this is I'm going to change the size of the bars to this. So I can do this pretty easily just by going over here and then changing the width. So I have the stat, position, identity, but let's just go ahead, let's change the width a little bit. Now I can change that to 0.5. And look, they're a lot smaller. So you can customize the bar size if you want. But you might also want to add some standard errors as well. So to do that, we can do that pretty quickly as well in here. So what we're just going to do is we're going to set the Y min for the standard error. So geom error bar is just going to be our standard error bars. And then we're just going to set that as ls mean minus the standard error from the data that we have. And then we are going to set the max equal to the ls mean plus the standard error. And let's just make sure that the width of these bars isn't too big. And so we'll set it to 0.2. And now we've got some nice standard error bars on top of our data. And so the list of things that we can do with these data are quite large. I have a number of these available for you to try out within the practice code that I have available. And there's a few different practice questions that you can go through as well, where I will take you through some different opportunities for you to use these data as well. But in terms of the gist of this is what I wanted to go over for right now in terms of using ggplot as a introduction, and then moving into the next one or the next tutorial, we will focus on using ggplot to create line graphs instead. So we did a little of that with just the plot function, but now we're going to focus on doing that with ggplot because that will provide us with some other really great opportunities. So stick around, we'll see you soon.